All right, so today's video, we're going to cover section 5.3 from our textbook, which is solving systems of linear equations using the third method that we know called elimination. So first, I want us just to point out that what we're doing is going to be something similar in idea or concept to the substitution method. And what we're doing in the substitution method is we're doing something with the original equations to be able to write this new equation that only had one variable in it. So just as a reminder, like in section 5.2, I just have an example prepared from the notes. We had this system, like negative x plus y, 3x plus y, all that stuff, and we isolated a variable. And what we were able to do is we were able to take that new or the isolated variable and plug it into the other equation. And then by doing that, we created this new equation that only had one variable in it. And that variable was just x. So we were able to solve for that x value. Once we found x, we could go back and plug that in for y. So we started with two equations with two variables, and we did something to create a new equation that only had one variable in it. Well, that's going to be similar to what we're going to do with elimination. But with elimination, we're going to accomplish this by adding or subtracting the equations to create a new one. What we're trying to do when we add or subtract them is to eliminate a variable so that there is, again, only one variable left. Now, since we're adding or subtracting equations, and our equations are of lines, I may call this, or other people may call this, the linear combination method, because we're combining lines to create a new line that only has one variable in it. So here's an outline of the steps that we're going to do through the examples today. But remember, our general goal, that is what we're going to try to do, is add or subtract some equations together so a variable disappears. What we want to first look for in step number one is to see if any pair of like terms has the same or the opposite coefficients. So like down here, I just want us to point out that when we're using the elimination or the linear combination method, our like terms need to be organized vertically. So like this is a 3x, that's a like term with this because they're both x's. Same thing with the y's. This 2y is organized vertically with those y's. And then at the end, numbers can be combined with numbers. So we organize our like terms vertically. What we're trying to do is eliminate one of them. And just as a reminder, something would be eliminated if it has a coefficient of 0. So what we want to look for is to see if any of them already have the same or the opposite coefficients. So like, let's just look at the x's. The x's have the same coefficient. They are both a 3. Now, once you identify coefficients that are the same or the opposites, you always want to ask yourself, what would I do to those? Would I add or subtract to get 0? So if I notice that x's have the same coefficient, 3x and 3x, what would I do with 3x and 3x to create 0 x's? Well, I'd subtract them. So if I'm going to subtract the x's, I will do that with all of the terms. So 3x minus 3x was 0x, 2y minus negative 2y, and just recall, we might need to do a little change. Minus a negative is just like adding a positive. So that's 4y. And then 4 minus negative 4 is 8. So by combining these two equations, we've created a new equation that only has one variable in it, right? I don't need to write 0 x's. I can just say this is 4y equal to 8. So just like with substitution, we did something and we created this new equation that only has one variable. So we can easily solve for y by dividing by 4, and we get y is equal to 2. So once I know what y is, just like we did with substitution, we plug that back in to find x. So I'm just going to plug it back into the first original. It doesn't matter which original you plug it back into. Instead of y, I'm going to replace that with the number 2. So 3x plus 4 is equal to 4, so we'll subtract 4. So 3 times what number was 0? Well, that number must have been 0. So in summary, we think that these two lines intersect at 0, 2. And that would be our final answer. Now, this is a method for solving systems of equations, so we can look at a graph to make sure that we're correct. So on the graph here, I do have the two lines prepared, 3x plus 2y equals 4, and 3x minus 2y equals negative 4. And when I see that they touch, the point of intersection is 0, 2. So again, just summarizing, we have another method to find the same answer. Now, what's important here is we're looking either for coefficients that have the same or opposite coefficients. So with the example we just did, I'm just recopying it here, we looked at the x's and we noticed that they had the same coefficient. And if they had the same coefficient, like 3 and 3, we subtracted them to get the x's to eliminate. But we could have also have noticed that the y's have opposite coefficients. So I could have asked myself, what would I have done with 2 and negative 2? To create a 0? Well, I would want to add add those together. So I could have also added these to eliminate y first. So 3x plus 3x is 6x, 2y plus negative 2y is 0y's, and 4 plus negative 4 is 0. So here I eliminated a different variable, but again, I notice that I've created this equation that only has one variable in it. So I do get x is equal to 0, and I would plug that in to find y. And we would get the same answer, so it doesn't matter if we're adding or subtracting these equations to get a variable to go away, as long as one of the variables does go away. So as we move forward, the way that they get harder is we'll notice, like with this one, if I analyze the like terms, like the x's are on top of the x's, but 3 and negative 6 can't be eliminated by adding or subtracting. Same thing if I look at the y's, positive 2y's and negative 5y's. Just by adding or subtracting 2 and negative 5, I can't get that to be a 0. So we might need to do a little setup work. Just like we did with the substitution method, sometimes we had to do a little work to get an equation to be ready for substitution. So like this one here, first I would have needed to subtract 3 x's, and then I would have needed to have divided everything by 2. And then I finally would have gotten my substitution ready to go. So that will happen with the elimination as well. We might need to do a pre-step or something before we're able to use the method. Now here we want to try to multiply the smallest number of things. And what I realized here is if I looked at this first equation, so I'm just going to put a number 1 next to it. So that's my first equation. I'll put a 2 next to this one. So when I talk about my second equation, you know what equation I'm talking about. So what I notice here, if I took my first equation and I multiplied it by 2, everything there being multiplied by 2, I'd create this new equation that would look like 6x's plus 4y equals negative 4. Now, I'm just going to recopy the red one below it, negative 6x plus 5y, or sorry, minus 5y, is equal to 2. So after I did a little setup work, I noticed now that the x's have opposite coefficients. So I'd ask myself, what would I do with 6 and negative 6 to get that to be a 0? Well, 6 plus negative 6 would be 0. So I'm going to add everything. So 4y plus negative 5y is negative 1y, and negative 4 plus 2 is negative 2. So again, I've created a new equation that only has one variable in it, so I could see that y was equal to 2. And after that, it's fairly straightforward again. Once I know what y is, I can plug it back in. So I'm just going to plug it back into the first one to find the x value. So here I get 3x plus 4 is equal to negative 2. So after we subtract 4, 3x is equal to negative 6. So x is equal to negative 2. Now, again, just to emphasize that we're using a method to solve, if I wasn't using a graph to check my work, I could plug this in for x and y to make sure that it satisfies both of the originals. So again, we think our solution is the point negative 2, 2. So if I plug it into the first one, 3 times 2 plus, oops, sorry, negative 2 times 2 times 2, does that equal negative 2? Well, yes, negative 6 plus 4 does equal negative 2, so it satisfies the first one. And we can see that it satisfies the second one as well if we plug in the x's and the y. Is 12 minus 10 equal to 2? Yes. Now, just as a closing here, I only multiplied the first one, and I chose to multiply the x, or to eliminate the x's, because to eliminate the y's, I would have had to multiply both equations by something. There's not one thing I can multiply 2 by to get it to cancel with a 5, and there's nothing I could multiply negative 5 by to get it to cancel with a 2. So I'm always looking to multiply the least number of things. In certain situations, though, I might have to multiply both of them. Again, here, if I looked at the x's, they're not the same or opposite. But if I multiply 4 by something, there's nothing that gives me a 6, and there's nothing that I could easily multiply 6 by to give me a 4. The same thing happens with the y's. Just multiplying one of these equations, I can't get the x's to have the same or opposite coefficients. So here we might need to multiply both of the equations. So in this case, we get to choose what we want to eliminate. So I choose to eliminate y. It wouldn't really matter here, but that's just the choice that I'm making. So if I wanted to eliminate y, these need to have the same or opposite coefficients. So 5 and 2, I could turn them both into a 10. So I'd multiply this first equation by 2, which would bring up this new 8x plus 10y equals negative 28. I'd multiply the second equation by 5 then, because when I take the 2y's and multiply it by 5, that turns into 10y's, and negative 32 times 5 is negative 160. So now, after setting up my problem, I can now notice that the y's have the same coefficient. So I'd ask myself, what would I do with 10y and 10y to create 0y's? Well, I would subtract them. So I'm going to subtract all the like terms. So 8x minus 30x is negative 22x. Negative 28 minus negative 160. And again, if we need a calculator, which I'm using just to verify I'm right, it's okay if you need that, but that is 132. So if I get rid of the y's because there's none there, I now have an equation that only has one variable in it. And if I divide by negative 22, I see that x is equal to negative 6. And again, once we know what x is, we should take that x value and plug it back into one of the originals to find y. I'm just choosing to plug it into the first one. So instead of x, we'll plug in negative 6. And we'll just solve for the missing y value. So after we add 24 to both sides, we see that 5y was equal to 10, so y is just equal to 2. So the solution to our system is the ordered pair negative 6, 2. Now again, this example is here to see that we'd have to multiply both of them. Now it would have been fine to eliminate the x's as well. If I would have eliminated the x's, 4 and 6 could have both been turned into a number like 12. So I could have multiplied everything by 3. And then with the second one, multiplied everything by 2. You could see here that we would go through the same process. If the x's had the same coefficient, 12 and 12 would be subtracted to create 0 x's. And we'd continue with that, and you would see that we get the same answer. And we just get them in a different order. I won't finish that out exactly, but it doesn't matter when we get rid of x or y. Now, the last part of the notes today is just to remind us that in order to use the elimination method, those like terms must be organized vertically. So part of our getting ready to eliminate, we might need to rearrange things. Like when I look here, the x's are not on top of each other, the y's are not on top of each other, and the numbers are not on top of each other. So I might need to rearrange things. Now, as it says in your notes here, you can use any order you want to rearrange things, but it's usually easiest just to use standard form of a line. So with that, once I notice that the like terms aren't on the same organization, like this first one, I want to turn it into standard form. So the x's need to come first. So I just rewrite that. I take the positive 9 x's and put them first. The negative 3y's would come second. Now with the red one, I need the x's and y's on the same side. So I'm going to add 6 x's. So that's one other thing we may need to watch out for when we're getting ready to use or set up for the elimination method. Now here, once I have all the like terms, so see how the numbers are now on top of each other, the x's are now on top of each other, and the y's are now on top of each other. So I can ask myself, are any of these ready to be eliminated? None of them have the same or opposite coefficients. So I'm going to try to multiply one of them to eliminate. So I can notice here I could multiply the bottom one by 3 to get 3x to be a 9x, or I could multiply the top one by 2 to get negative 3y to be negative 6y. It doesn't matter which one we do. For the case of this video, I'm going to choose to multiply the second one by 3. So if I multiply the second one by 3, that creates this new equation, 9x plus 18y is equal to 6. And then I'm just going to recopy the original first one, 9x minus 3y is equal to 20. So now, once I notice that the x's have the same coefficient, I'd ask myself, what would I do with 9 and 9 to create 0? I'd subtract them. So I'm going to subtract everything. So 18 minus negative 3. Remember, you might need to show a little side work to see that we change that to a plus plus. And then 6 minus 20 is negative 14. So now we've created this equation that only has one variable, so dividing by 21. And then simplifying, they're both divisible by 7, so we get y is negative 2/3. Once we know what y is, we should plug it back in, and I always think or recommend we should plug it back into an original equation. So I'm going to use the red original equation, because if I'm looking for x, that equation almost has x by itself. So instead of y, we're going to write down that we think y is negative 2/3. So we get 3x is equal to 2. Now a negative times a negative will be a positive. 6 times 2 is 12. 1 times 3 is 3. So this is 3x is equal to 2 plus 4. So we get 3x is equal to 6. So x must have been equal to 2. So our final solution, these two lines intersect at the point 2 and negative 2/3 for the y value. And again, we could check on a graph or we could plug it back in. So that's how we're solving with elimination. Just summarizing, our main goal here was to either look to see if the coefficients were the same or the opposite so that we could add or subtract terms to make one of them disappear. If we notice that the coefficients on x or y either weren't the same or weren't the opposite, it might be necessary to multiply one or both of them so that when we do that, we do see the same or opposite coefficients. Then we're either adding or subtracting them to eliminate a variable, solving for that variable, and then using that variable to solve for the remaining missing one.